Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 5, Section 2, and we're in Part 4. Just a quick review of some Part 3 things. We know that elements have different properties and the electrons are responsible for this, and we're wondering why electrons behave the way they do, and the answer lies in quantum mechanics, quantum theory, which is when things are super teeny. And this gives each electrons a quantum state, like an energy level and a position. And electrons are weird. Mass, size, location are spread out in a wave instead of just being a particle. And when they're inside of an atom, their wave properties are such a way that their energy level is the lowest. So they're going to fill the lowest energy level first. And each little place is considered a quantum state, and there can only be one electron. And they're never in between, they're always in one or the other, and there are never two. Okay, so we talked about light, and electrons are both particles and waves. They act like waves and they act like particles. And we know that waves have frequencies, they have wavelengths, and they have energy levels. And we looked at some of the constants in the universe are the same between electrons and light, because there's a lot of there's a lot of overlap there. And we know that you can add waves to make a larger wave, and waves can actually cancel each other out. So if the crest of one and the trough of another are lined up, then they will cancel each other out. And we looked at if there was a wave in a box, if its reflection canceled it out, it would just cancel out like this. So waves that exactly fit in the box with their own reflection. So if this wavelength fits in its reflection, it's going to add, but if it doesn't fit, then its reflection is going to cancel it out. So then it's like there isn't, the energy level would be zero. So what does this have to do with the electrons? Well, we could use this analogy of waves in a box for electrons in an atom. So you can see that there's this wave of an electron and it bounces back and that fits. Well, a little bit more energy, a little faster, doesn't fit, so it can't be in that energy level. But if you do a little faster than that, well then it's exactly the right size, it fits, reflection will reflect back. In a little faster than that, that's allowed, but even faster than that, well, that's not allowed because that's going to cancel themselves out. So that's just like electrons, where these 1, 2, 3 are allowed, but the electrons will never be found in these red states. And we know that the wavelength is related to energy, so a higher wavelength has more energy. So this one has more energy than that one. And that is why only certain energy levels of electrons are allowed. So this would be the lowest energy state, middle, and then the highest energy state. And the electron will only be here or here or here. But you don't find it here because we know that it cancels itself out. And these different quantum states have different energy levels, which means they have different wavelengths. And the energy wave for, let's say, the 2p orbital, there are 3 different orientations of that wave, like X, Y, and Z, and so that's why we get those 3. Okay, so you don't need to write this down, but do pay attention. Electrons kind of act like waves, and they carry energy and have a frequency and a wavelength. We know these things about waves. And we know shorter wavelengths have higher frequency waves, and higher frequency waves carry more energy. And then the wavelength of an electron must be a multiple of the size of the atom. Otherwise, those electron waves and their reflections just cancel each other out. And it's like that, it can't be at that spot. It has to be from here or here, but not in between. And a quantum state is one of the allowed wavelengths of an atom. And each quantum state has a specific energy, because we know the wavelengths correspond to energy. So please do write this down. Electrons fill quantum states from the lowest up to the highest energy level. And then there was this guy, Dr. Pauli, came up with the exclusion principle in the 20s that states that two electrons in the same atom cannot be in the same quantum state. It just does not happen. So the Pauli exclusion principle, two electrons in the same atom cannot be in the same quantum state. Also, you don't need to write these down, but please pay attention. So we know electrons have properties of mass, charge, and then this thing we haven't talked about, which is spin, which is kind of like clockwise and counterclockwise, but more complicated, and the way we talk about it is an upspin and a downspin. Also, Heisenberg's uncertainty principle. So Dr. Heisenberg studied electrons and waves and all this stuff in the early 1900s. And so what this principle says is that you can't know the velocity and the position of an electron. They're just zipping around, and once you observe it, so you know its position, then you have interacted with it, so then you kind of like change its velocity. You like make it bump into whatever you're using to observe it and then fly away. So if you observe it then and know its position, then you change its velocity, so then everything else changes. So there will always be uncertainty with electrons. Also, you may have heard of Schrodinger's cat. Dr. Schrodinger was a famous chemist in the early 1900s, also working on like electrons and waves and stuff like that. This was a thought experiment that tiny particles can be in two states at once until they're observed. And you're like, well, where does the cat come in there? Well, it was this whole complicated thought experiment where there was a cat in a box, and there was also like cyanide, I think, and then there was like a radioactive particle, and when like the uranium, if a uranium atom decayed, it would hit a sensor that would break open this container of cyanide, and it would kill the cat. And if it didn't, then the cat was alive, and then like the theory would be the cat would be both alive and dead until you opened the top to the container and observed it was either alive or it was dead, but before then it was both. So electrons don't act like cats, but electrons are way more complicated than cats. That was kind of the point of the experiment. The thought experiment. There were no cats hurt in this Schrodinger's cat thought experiment. All right, so let's kind of see where we were with the Pauli exclusion principle. We're here in the early 1900s. We've already done all of the other things we've talked about. Democritus, the idea of atoms, Dalton's atomic theory, J.J. Thomson discovering the electron, Rutherford discovering the nucleus in the gold foil experiment. So that's where we're at. Let's quick talk about lithium. So we know lithium has 3 electrons, and we know electrons need to fill the lowest energy level first. So the first 2 go into this first energy level, and then there's 1 up in the next energy level. So just a quick summary. Electrons are arranged in a pattern according to their energy levels. The lowest energy levels are always filled first. There's only 1 energy level, 1 electron per quantum state. And lithium's 3 electrons go into 2 into the first energy level and 1 into the second energy level. And that we know that energy is quantized. It's a quantity, so it could be, electrons could be in this one, or this one, or that one. All right, that is 5.2. I will see you later. Bye.